Be right back. I just got to refresh my glass of water.
Michelle's just jumping back in there. So.
Hey, JJ, can you hear me?
Yes, you're back.
Yeah, back from lunch.
Yep. Right, Stephen and Michelle, are you good to answer a question from Rab Carrigan? Stephen, you're there?
Yeah, I'm here. I'm just going to send that question out again in the chat.
Yep.
So everyone can see it and Michelle can see it. And then we can have a little conversation with Rab.
Okay.
Stand by there, Dino.
Hey, no problem, Steve.
So Rab's question was, we have a glycol heating loop that feeds our air handling unit coils in one of our buildings. It has a triple duty valve on the pumps, and the pumps are on VFDs, but the system is controlled by a valve. Is that another valve beyond the triple duty valve, but by a valve using differential pressure? What would be the best way to run this? And Rab, you've mentioned that the drives are running at a constant speed right now, correct?
Correct, yeah.
Now, are they at full speed, part speed?
Part speed, that's why I was trying to access the BAS from remotely to see what they're doing right now, but I couldn't get in with IT issues.
Yeah, so the control valve that's using differential pressure, that's separate from the triple duty valve, correct?
Correct, it's actually across a bypass. If you imagine a bypass.
Well, that's yeah,
Okay,
so you really need to increase that bypass valve pressure way up. And then what you're going to do, you're going to drive the VFD based on the differential pressure that the bypass used to keep. So now you'll have a real variable flow system. So the VFD will replace the bypass valve as your pressure differential controller. If you want to go even further, you could actually do what's called valve reset. I'm not going to go into details, but if your BAS is like full DDC and you know your AHU valve position, you can actually reset the set point for your VFD to force at least one valve to be fully open. So that set point that right now you're keeping using that bypass valve, that set point, you can transfer it to the VFD and really use the bypass just as a safety. Make sure that it has a higher set point so it doesn't really come into play unless there's an issue with the VFD. But then the set point itself, you could reset it based on your AHU valve position to ensure that at least one valve on your AHUs is fully open. Because if it's not the case, it means your set point is too high for no reason.
Yeah, I saw that similar situation in another building recently, and the savings were pretty dramatic. So it sounds like there's some good opportunity there.
And
Yeah, thanks for that,
if you
Michelle.
want that,
That's
if you
to
want
me
that in,
really good.
I was going to say, if you want that, like in an email, like because right now I'm just giving it to you verbally. Either send Steve or myself an email, and we'll write that same answer we gave you. We'll write that out, and either yourself or control contractor can program that in for you.
Excellent. Thank you very much for that.
Great. So, I mean, for those who aren't super familiar with the situation, I know a couple of people asked about that. So the idea is to replace the valve, essentially set the differential pressure high, and then use the valve or the drive to maintain the differential pressure at the appropriate value using a pressure sensor to the drive. So. All right. So I think we're pretty close to 1 o'clock there, JJ.
Yeah, I think we are too. So do you want to jump into the next session?
Yeah, just going to confirm. We got a minute to go. Dino, are you all ready to go there?
Ready to go, Steve.
Okay.
Okay,
So,
good stuff. We'll just give folks a few more seconds to log on, and
I'm not actually seeing the cam. Can you see my camera?
yes.
I can see you, Steve, and I can see JJ.
Okay, cool. There we go. Everyone. I must have my cameras hiding somewhere. There we go. Even when you use this thing many days a year, you can get messed up.
Well,
Okay, we've had a few more people log on, so we'll get things started. Welcome back to Energy Light, and it's Module 8 that we're going to start the afternoon off with, and that's compressor systems. And with us today, we have a subject matter expert, and his name is Dino De Filippis, and he's from his company, Airnergy. Dino is a certified energy manager and a certified engineering technologist, and he has over 35 years experience in the compressed air industry, starting as a service technician, and then that led up to operating his own compressor company for 20 years. He's worked with and on virtually every make and model of air compressor in the industry. For the last 15 years, he's been heavily involved in compressed air audits, assisting customers with realizing true energy savings without the capital investment of purchasing new compressors, but rather assisting them in implementing proper PM schedules, preventive maintenance schedules, leak detection programs, and demonstrating numerous best practices to reduce their electrical operating savings, or reduce their costs, I should say. He has worked with many customers, both nationally and internationally, directly and through local utility providers, using both audit incentives and project retrofit programs. Dino is going to tell us what he sees as the key to understanding actual compressed air system performance, true supply and demand, and the system's overall health. Over to you, Dino.
JJ, thank you very much for the introduction and the opportunity to assist with this workshop. So as JJ had mentioned, what I usually do is in the compressed air audits is analyze the systems as a whole. Let me see. I'm just trying to get this screen to move forward now. I've been sitting here for. The screen's not moving forward.
Oh, put your mouse onto the slide on your second screen. Click on it, right? And then
Yep.
you right arrow key and it'll, there you go. Okay.
Got it. My apologies. I'm not as proficient as Steve is on here. So when we look at compressed air and the opportunities, why do we look at, well, compressed air? It's one of the major consumers of electrical to run motors. Utility costs are on a rise. A lot of customers looking at upgrading compressors or expanding an existing system. They don't know how to go about fixing it other than purchasing a new compressor. An efficient compressor purchase does not necessarily mean that the system is efficient overall. And I think that's one of the things I've found over the last 15, 20 years with the introduction of VFD compressors, that once customers install these particular makes and models, that they believe the system is working at peak efficiency. And in fact, they've left a lot of energy waste on the table and money, and that I usually go in there and find what needs to be done properly before ever replacing compressors. Obviously, the larger the system, the more complex, the larger the opportunity when it comes to savings. Most compressor companies are only involved in or concerned about selling new compressors, while the supply side is only a minor part of the energy savings. The demand side is where the actual reduction in energy occurs, because that all translates back to how the compressors operate. We need to, so obviously the larger the system, you can see that there's a lot of components in it that needs to be looked at in detail. If you're doing a study and you're looking at upgrading a system or simply reducing energy costs. And the majority of the times, customers are not monitoring or measuring power consumptions and pressures and flow and so on and so forth. Even air quality is something that's always neglected in many industries. So some of the simple things without having to buy equipment is just to identify what you can control and you can't control. And those 6 items there are the ones that simply will give you the biggest bang for the buck and the greatest return on an effort put into it, such as the controls on compressors, the pressure you run the system, the leaks that are within the system, maintenance or lack of on the compressors, the distribution, and finally, how you actually use the air. All these come into effect if you're ever looking at upgrading the system or actually upgrading the compressor. And again, most of the times from a supplier, equipment supplier, they're only concerned about just selling the compressors. So I want to just give you a quick idea.
Can I jump in for a second, Dino? So
absolutely, and I forgot to mention, Stephen, if anybody has a question, by all means, just jump right in. They don't have to wait till the end.
So I just want to assure people that even though your previous slide of the picture kind of looked like an industrial situation, you have some examples coming up from hospitals. So a lot of things you're going to say are very relevant in healthcare as well.
That's correct. Some of these slides and graphs are from an industrial point of view. There are some case studies at the end which are healthcare related. This particular slide simply shows a customer who had some large 75 horsepower air compressors, 3 of them, and they were looking at purchasing another machine. And what I basically done was, in the first day, looked at how the compressors were operating. And you notice in the pre-adjustment section, we have a VFD there in the orange, and the other 2 fixed speed are kind of hunting and fighting each other. After I made the adjustments to the pressure settings, we actually dropped 1 compressor out of the loop. The fixed speed in blue was running continuously while the VFD was trimming. So in essence, the customer basically saved himself the cost of purchasing a 75 horsepower. He had now redundancy, and he's got 2 compressors running with 75 as the backup. So these are things simply from a controls point of view in a multiple compressor situation, regardless of the industry. All the compressors need to communicate with one another, and they need to be set up properly. Pressure is another one. Regardless of the industry, if you operate a system at an unnecessarily high pressure, that's a major waste of energy. I've found applications where, as you can see, pressure regulators are indicated to be set at a certain pressure, and customers and users and mechanics all ramp those pressures up unnecessarily for some issues, such as a plug filter in a wrong connection sizes, so on and so forth. So by increasing the system pressure at the compressor point of view, we're actually increasing the artificial demand. So the air consumption on leaks, the air consumptions through regulators, all this is increased by, I guess, inaccurately compensating for poor designs. And the first thing a lot of them will do is increase the pressures on the compressors. Leaks is another, well, it's probably the major one when it comes to plants, whether, obviously the larger the plant, the more complex the distribution system, and the age of the plant, I find a considerable amount of leaks. So leak tagging and a leak audit, I normally recommend the customers to be done, depending on the size of the plant, every 6 months, possibly once a year, with an ultrasonic leak detection. And that picture and a couple of other pictures, and I don't want to show you all 100 of them, repairing leaks. I've seen everything from duct tape to rubber gloves to electrical tape in an attempt to fix leaks. And that's just not the way to go. There has to be an aggressive leak repair program. But leaks are probably the number one low issue for artificial demand, and it's the low-hanging fruit. Everyone should be doing that. Maintenance is another issue, and believe it or not, lack of proper maintenance on a compressor, whether it's reciprocating or screw, does affect the performance and the kW demand on the compressor itself, such as differential pressures across my intake filters. As you can see, this one is completely plugged, so this compressor was starving itself. High differentials across filter elements. Filter elements, point of use filters, inline filters, all need to be part of a regular PM program. Not just changing oil on a compressor, but everything associated that comes down to pressure restrictions and back pressure. So it's important that customers follow a PM schedule specifically to their compressor, in-house daily checks, weekly checks on things such as the dryers, the filters, the drains, make sure they're all working properly. And again, all point of use filters are replaced on a regular basis. They're always been neglected, those little point of use filters. And distribution. I can't say enough about distribution, as usually pipe systems and branches and loops are installed years when plants are manufactured or utilities are installed, and then as plants continue to grow, more and more compressors and equipment are added, and yet the piping distribution is always kept the same. Keep the piping diameters as large as possible. A loop system, a closed loop, is much better than a branch. If you've got a branch system, just ensure that the diameter is as large as possible. Satellite tanks at the farthest point or the largest consumer of air when equipment starts up is a good practice. And obviously try to avoid too many elbows, T's, and so on and so forth. Just simply keep it simple. This particular graph here was a classic because the customer was running all his compressors at 120 pounds or so. But at the point of use, he almost had about 80 pounds, a 30 to 40 pound drop in the system. He was about to drop a few $100,000 on a brand new compressor, and the problem was his piping was just inadequate to supply that much air to a point of use packaging system. So that's where we put simply pressure loggers in real time that will register pressure at the compressors, point of use, and throughout the distribution, and that's where we were able to catch. You had no problems with the compressors, it was this piping system that was too small. End uses, avoid too many elbows, T's, I had mentioned, keep it simple. Point of use regulators where there are none. We don't need to drive a system to 100 pounds at the point of use, or 90 psi. If we can get 60 or 70 at the point of use to operate a couple of controls, that's great. With our regulators in place, make sure that they're set as low as possible. Facilities that use air guns, even in the workshops, make sure that they're high efficiency air guns, same as nozzles and other devices, and vacuum pumps rather than vacuum generators. This is just a tip of the iceberg of some practices that can be used, installed to replace compressed air and save on energy costs. So we look at other ways when it comes to compressed air systems. We've got, do we consider air-cooled compressors versus water-cooled? Can we look at heat recovery? Can we use some of that water-cooled on a compressor for feed water to a boiler? Drying systems, what is the minimum requirement of the compressed air dew point? Do we need a desiccant dryer? Do we need a refrigerant dryer? Are we looking for oil-free, general purpose air? There's so many questions to ask when it comes to drying systems, and yet they all affect how the compressors work and the air quality that goes to these controls. Multiple compressors, so many plants have smaller multiple compressors located throughout the facility. Will one compressor do the work? Consider possibly a central compressor room. At the same time, consider a central compressor controller that will manage all the compressors simultaneously rather than having a pressure cascade where we set 3 or 4 compressors all at different pressure settings in case one fails and so on and so forth. That range or that pressure cascade is a large waste of energy because we have to drive the last compressor to the highest pressure to compensate for a failure, where a central sequencer or controller has a tighter pressure band, so we can operate 3 or 4 compressors within 2 or 3 psi. And then obviously look at pneumatic versus digital controls. Many of the hospitals I've worked at have now converted their pneumatic HVAC controls and louvers to electrical. Same with the valves and steam, water, and so on and so forth. And all these P&ID loops that they all talk about, many of them have converted again from pneumatic to electrical. So helpful hints when it comes to systems is control the leaks, stay on top of the PMs. You don't want compressors failing because someone's forgotten to change the oil or top up with oil. Regular filter replacements, maintain proper cooling of the intercoolers and aftercoolers, and ensure that the air originates from a clean, dry, cool locations. Too many times I've seen compressors stuck in the corner of a boiler room, and they continuously fail because of the high atmospheric temperatures. They virtually cook the oil inside the screws, and they also affect any type of drying systems, whether it's desiccant or refrigerated. Sitting inside a boiler room that's not properly ventilated, you continuously run into issues. So here's 3 case studies that I just want to quickly go over. The first one is there was a hospital that had some large compressors. I just want to, so they've got 250 horsepower oil-free, water-cooled rotary screw compressors, and that's how much air they deliver each. The issue we had found, and this was obviously sold by a compressor company, that each compressor was only operating at half capacity. You can see where I've got first one's at 51% and 48%, and they were loaded, stopped and unloaded at the virtually the same time. The annual cost to run these 2 compressors as is was about $77,000. We identified about $37,000 energy savings through pressure reduction, leaks, and dryer purge reductions. The dryers are desiccant type on 655 SCFM, so every time they purged and regenerated, it was almost 15% of that was about 100 SCFM they were using just on the purge on desiccant dryers, which they didn't need that type of drying system refrigerated would have done. But there was an opportunity there to reduce those that purge reduction in energy costs. The second case study was another hospital that had 2 50 horsepower oil lubricated air compressors. The average output on a 50 horsepower is about 200 SCFM, but the average actually used in demand was only about 115. And neither one of these compressors are actually ever worked at full capacity. So these were oversized compressors for what this hospital needed. Annual cost on these two compressors running as they were was about $31,000. We identified 15,000 just in pressure reduction leaks and properly sized compressors. And if memory serves me correct, they went through a retrofit project and installed two 25 horsepower units to run the plant, and one is the redundancy for the second one. So they were able to drop the horsepower to half of what they originally had, and had a considerable savings from the IESO on the retrofit program. This particular case study was a large pharmaceutical company, and they had, again, some large 100 horsepower oil-free air compressors delivering about 392. The problem they had was that these oil-frees were connected to a common 2-inch header, and they had continuously pressure drop issues all the time, especially when these desiccant dryers began to purge. What I've done with this photo, and you can just make them out, is that all these X's I've marked are on the piping restrictions on T's and elbows, and I think we counted about 15 elbows from the compressors by the time it came out of the compressors right to the dryer. That's their pressure loss. They had about a 20-pound pressure loss just across the system because the piping was incorrect. They had both dryers online simultaneously purging when only one was required. So there was it was excessive purging on a second dryer that wasn't necessarily. So out of the operating cost of $114,000 per year to run these two compressors, we identified 44 in energy savings through pressure reductions, leaks, storage, and proper piping. No other requirements in the system, such as new compressor, storage tanks, so on and so forth. This is the exact same customer. What I pointed out to the customer after 10 years of him having the system in place is that on the name tag of the compressor itself, it specifically says, be sure to provide an air receiver of the required capacity downstream of the compressor. There was none. These compressors fed directly into the dryers, which affected how these compressors operated. And we can see that both by that power graph chart, that both compressors are basically fighting each other as they're loading, unloading, or one's loading, and so on and so forth. Orange and blue are the two 100 horsepower. So improper storage, incorrect piping, had two compressors on all the time, simply fighting each other because of the back pressure created on this. And I believe they've increased their pipe size to a common header, installed a tank, and they're good to go. So these are the sort of things that we find out in the industry. So it isn't necessarily buying an efficient compressor get you an efficient system. None of the cases I've ever worked on, other than possibly a handful of 5 customers, required new compressors. It was all the quick fixes, the control settings, pressure, piping, storage, so on and so forth. And some larger ones, the killer was the leaks. That's primarily it for my session here, and I'm more than happy to answer any questions anyone may have.
That's great. That's great, Dino. I think there was a lot of good meat in there. I was interesting that you actually cut the cost of operating the compressed air system in that one hospital in half, basically, right?
That's correct.
You got a pretty good incentive for it. It's funny because instinctively I wouldn't have thought about that, but yeah. So, folks out there, questions, maybe some stories that you've run into with your compressed air systems. Have you started to look at your compressed air systems, or is that just something that operates?
You know, I have one question in the meantime. It's JJ. I just wonder if you can share with people what typically would be the incentive for you coming in and doing an audit of the facility of the compressed air systems.
Unfortunately, JJ, the Save on Energy and the ISO cut the funding for compressed air audits. They wiped them right across the board on everything. The retrofits are still available. So if the customer's looking at upgrading a compressor system or storage or piping or so on and so forth, Normally what I tell the customer is that they can put the audit costs against a retrofit and claim it as a project management cost, which is allowable. But the initial incentive, unfortunately, there isn't any, and which was upsetting to me, to be honest with you. But if a customer is looking at having their plant reviewed, I have no issues in making a courtesy visit to the customer, doing a once over the compressor system, giving them a few ideas, and if they want to pursue a more detailed analysis like this, then that's something we can discuss. But I built a good relationship with customers, just helping them out and pointing them in the right direction. So I certainly have no issues in visiting any customer when it comes to compressed air.
Yeah, regardless of incentive, needless to say, the cost to do an audit is probably recovered in short time, given the magnitude of the savings that you're finding in most of these systems.
Oh, absolutely. That's the question I get. So we pay for an audit. How much do we get? Like, what's the incentive? Like, what's the return on it? And I go, well, there's some basic rules of thumb there. For every pressure drop I can save you, there's a percentage of your energy savings. Take 10% of your flow rate and energy costs is for leaks. That's a quick number you can calculate out. Best practices is another sort of rule of thumb out there at 5% of your energy costs. So yeah, for normally health, like what I've done in hospitals, it's normally 2 days at best to go through their plant with an analysis. Sometimes 3 days with an ultrasonic leak detector. Yeah, that's all paid back just by identifying leaks and implementing some best practices within. The return is a quick payback, to be honest with you.
Right.
Yeah, for those that aren't in Ontario, maybe that would be able to take advantage of Dino's services, there are obviously other compressed air providers across the country. And I think the thing I want to point out, I worked with Dino in a number of situations. I once brought him in a project on an industrial set of audits, and the customer was ecstatic with what he did because he didn't, then again, recommend a new compressor. So if you're going out looking for a consultant or someone, what you want is someone who's going to sort of do what Dino does. You don't want the supplier of the compressor systems. You want someone who's going to look at it objectively and really understand what it's doing. I think that's critical. So it's interesting, Dino. I've even talking about pressure drops. The same thing goes for many kinds of systems, but I've even seen in compressed air where you've got two compressors coming up to a header, and then the lines go like this, and then it goes out. That's the feed to the plant, and the air from those two compressors collide at that corner, right, which is a hard corner, and that's a pressure drop into itself, is it not?
And that's correct, and that's that last photo I showed you with those 15 piping irregularities. We don't tee into compressors together. We increase pipe size. So in this particular case, if you got let's say you got some smaller compressors, both 1 inch. If I connect those two, I want to upsize that pipe to 2. I don't want to continue that pipe size with 1 inch. I just want to continue with the larger pipe size. I want to reduce that restriction. I want to put storage after the compressors. Not filter elements, filter assemblies. Obviously, compressor suppliers want to sell you more filter assemblies for replacements. And to me, a storage tank works wonders. So those are just some best techniques that I look for. Piping, proper storage, proper filtration, proper drying, and so on and so forth. And it is compressor systems can be quite simple, and yet they're made so complicated and complex that nobody realizes where the waste of energy is in an improperly designed system.
Yeah, so for folks out there, if you just take a walk through your room tomorrow, where there's the boiler room, wherever your compressors are, look for those hard 90s. Ask the question: do we have receiver capacity? I'm not saying you don't, but you never know. And you've seen it many times over. If we have multiple compressors, are they running effectively in sequence with one another? Or if you've got a varying demand, do the compressors follow that demand, or do they just run in parallel? Because sometimes those controls, if they're running basically together, those compressors in modulating control don't know how to get out of their own way and can use a high percentage of full power, even when they're producing a small amount of air. So there's some simple things people could do just to get an idea of whether they actually have some opportunities, right?
That's correct. And I didn't get into too much details about the different types of load mechanisms, but you did mention it. The most efficient compressor you could run is a VFD. The second is a load-unload machine. But if you have an air compressor that's set in a modulating mode, and there are some mixing models out there that's all they do, those are the type of machines you want to get away from, because at minimal capacity, they're consuming anywhere from 70–80% of their total kW. So if you've got Gardner Denvers and Quincy's and Solairs, make sure that they're set in load-unload mode as opposed to modulation. Modulation has a benefit of a more smoother pressure delivery, but from an energy point of view, it can be compensated by putting a storage tank there and simply having the compressor load and unload.
We have a question on the chat line. It's maybe a bit out of topic. Not sure what your experiences is with medical gas systems, but do you think there's a benefit to tankless vacuum pump systems?
It is slightly outside my expertise. I've been in hospitals where I've seen vacuum pumps, but the majority I've always seen with some sort of an accumulator or a tank on that.
Right.
In that particular case, I'd probably go to the experts, and that would be the vacuum equipment manufacturer. But I've never seen a tankless, to be honest. I've always seen vacuum tanks in hospitals.
Right.
I just put a couple of links in the chat there. There's one it's an Enercan guide on compressed air, and there's another one from the Compressed Air Challenge in the US. There's sort of best practices and a few checklists in there. Something people go look at. So,
and those two, the Compressed Air Challenge is a good encyclopedia where you can get a lot of information on implementing some best practices and what to look for. It is as thick as the Bible, but there are some good things that you can get from there.
I'll just put a link to the actual library there with all the other documents, which is very thick.
Yeah.
One more question. You made reference to data collection around compressor systems. So in your opinion, what's the best way to collect and track data related to compressor systems?
Well, when it comes to an audit, there's power meters, flow meters, pressure transducers that we put throughout the distribution system. That data is uploaded onto the device and then uploaded to an iCloud, and that's where I get all my analysis from. However, that's 2 weeks of data collection. Once it comes off, I can tell the customer the good and the bad news. However, what I really stress that customers should put some sort of a monitoring system where they can monitor pressure and dew point and flow and power and pressure on their system 24/7 in real time, and they can watch it on their computer screen. It'll alarm when there's any issues. I always try to tell customers monitoring is probably, it'll start flagging when things start going wrong, and that's when you want to catch it. There's some expensive units out there that are from the equipment supplier. There are other suppliers that can provide monitoring equipment for compressed air. It's something they could look into if it's of interest. Most healthcare facilities I've been to in hospitals, they got a central control room where they're monitoring their HVAC systems and their boilers and their chillers, and yet the compressors are simply just turned on and run without any idea of what they're doing and what they're not doing. So I don't understand sometimes why not the compressors.
Yeah, I hear you on that.
Was there a question there?
Yes, sorry. Do you see a lot of water-cooled compressor in hospitals?
Sorry.
Michelle asked, do you see a lot of water-cooled compressors in hospitals?
The hospitals I've done about 6 of them. I've seen 3 water-cooled systems. And the rest were air-cooled.
Yeah, so that opens the door for heat recovery if you have water-cooled compressors.
Yeah, on the water-cooled side, like actually those 2 150 horsepower machines were both water-cooled, and they were using city water, and it was coming into the compressor, and they dumped it right to drain. And I said, this is ridiculous. We should recover some of this water. send it to your boilers, your feed water, goes to some heat exchangers, use it for space space heating through a couple of rads. There's a lot of opportunities for water cooled. There's benefits to it and there's disadvantages, but it all depends. You've just got to weigh what sort of water treatment you've got in house, so on and so forth. You're on a closed loop. Air cooled are fine too. Just got to watch where you're putting these air cooled machines, not in the boiler rooms, not beside a boiler, so on and so forth. So there's pros and cons of every machine I've seen out there.
And making sure your outside air intake is out, like your fresh air or your air intake is outside the heated area or the humid area too.
Well, that's correct. And another hospital downtown Toronto was their fresh air intake to the compressors was actually right beside the receiving door where the transport's backed up, and they were pulling in carbon monoxide, and it was causing issues. So good point, Steve. Watch where you're pulling the fresh air. From a rooftop, it's great, not from a parking lot.
Well, it doesn't look like we have any more questions. That's great, Dino. I appreciate that. I've done a lot of work in compressed air and industry, and actually, I never really thought that there would be that much opportunity in a hospital, but you've clearly changed my perspective on that one.
Yeah, the larger the utility, obviously the larger the payback. Even the smaller ones, it's just a tweak here and a tweak there. So there's always opportunities when it comes compressed air. You got to try to get as much out of it as possible. So if anybody has any questions, they can reach out to you, Steve. You can let me know. And JJ and Steve, I appreciate the opportunity to help you guys out. Look forward to helping you out in the future.
That's great. Thank you, Jay. Dino, could you just put your contact information in the chat there for folks too? All right.
I can. I feel like.
Once I stop presenting, you can do it. Once I start on the next section, you can do it. How's that?
Perfect. Okay. All right. Yeah. Because I don't want to mess things up. So I'll leave my contact information in that chat thing.
Okay.
All right. Thanks, Steve. JJ, thank you.
Yeah, thanks a lot, Dino. It sounds to me like there's a lot of return that could happen with very little investment up front. So I think that's what everybody's looking for, is for a good project idea like that.
Absolutely, I agree.
Yeah. All right. So moving on, we're on to module 9, building envelope.